don't think I gave you a full set of reasons why we care about this. In my mind, actually, or at least it should be in my mind now that I've been thinking when reading about this, is that there are really probably 3 different reasons that in any kind of data mining problem, and this is not just for clustering. You could imagine covering this material in Jeff's class or in Vivek's class or anyone else's class. There are 3 different reasons why you need to worry about this problem of dimensionality reduction or feature mapping or whatever we call it. And the one reason, of course, is a visualization reason. So reason number one. So reason number 1, of course, is to visualize. And this is a very clear kind of problem. I want to look at the output of my clustering. And I'm going to say clustering here because we're in a clustering class, but you can, of course, replace the word clustering with whatever data problem you have. I want to look at the result of my clustering in 2 or 3 dimensions till we get our holographic viewers. That's about all we can live with right now. So in 2 or 3 dimensions, I need to look at the answers. My data lives in 100,000 million dimensions. What do I do? So that's an immediate reason why we need to do something. And of course, it's going to be really horrible because it's very hard to visualize things beyond 2 or 3 dimensions. In fact, there's a big open problem in Viz itself. We talked to the Viz folks, I'll tell you that. But we want to do something at least, and so there's been tools for it. The second reason is of course to be efficient. Right? So to visualize, sort of make efficient. And this goes back to the whole cursive dimensionality thing. Right? So how many of you are in Vivek's class? So I know he did a long thing yesterday about cursive dimensionality.
Yes.
Yeah. So this is slightly different. In fact, I was talking to him after this about that. And from his perspective, I think the cursive dimensionality is a modeling problem. The data looks strange in a high-dimensional space. I think that's what he was talking about. That things you expect to happen don't happen. From my perspective, at least from the perspective that I'm talking about here, there's a computational thing to this, right? And actually, you probably have seen that for pretty much any interesting problem that you want to solve, if you want to solve it exactly, it will take time that's exponential in dimension. Okay? So forgetting all the modeling issues, forgetting the meaninglessness of what you compute, the very fact that you want to compute it, it is going to be something that's going to be exponential in D. And if D is 100, this is basically hopeless. So there are many tools, of course, to try and reduce dimensionality of the problem while keeping whatever features you want intact. And that's what this is all about. Right? Dimensionality reduction and embeddings are general ways of making things more efficient. Now, dimensionality reduction is again just going from high dimensions to low dimensions, but keeping the underlying geometry of the space the same. That's a very specific kind of embedding. There are other ways to do embedding. Say, I have a graph problem. My problem is NP hard on graphs. I can't solve it. I'm going to embed the graph into a tree with the distances preserved up to some approximation. Why? Oh, because my problem is not NP hard in a tree, and I can solve it. So this idea of mapping something from one space to another, where the problem becomes easier to solve computationally, not even from a modeling point of view, is a notion that appears in many different places. Right? So we look at it here traditionally from the point of view of getting to a Euclidean space, because Euclidean spaces are nice, but there are many other ways to think about this. Okay, so I want you to keep that in mind, that there's a general abstract way of thinking about embeddings, not just in terms of dimensional. And I think the final thing, and this goes back again to Vivek's point about high-dimensional spaces, is that, and this I didn't mention last time, is that it might actually be that the true structure of your data is low-dimensional. So for example, a simple example of this is that if I have data in 3 dimensions, right, but actually all the data lies in some little curves here. What I'm saying is that the intrinsic dimensionality of the data is 1. Because it lies in a one-dimensional manifold inside this 3-dimensional space. And a lot of recent work in data mining, clustering, and other areas has been about, can we design algorithms whose running time depends not on the ambient dimension of the space, the 3 here, but the intrinsic dimension of the space, the 1. Right? And this, of course, is a big deal. If I have data in 100,000 dimensions, but I really only believe that 10 of them are interesting, I don't know which 10. I can either try to find those 10 directly, work very hard, or I can say, no, I don't care. I just want to design my algorithm so that it will only depend on the intrinsic dimension of it. Right? So this is another reason why you want to do dimension, because you hope to be able to extract the intrinsic structure. And this gets into things like manifold embeddings that I probably will not talk about in this class, but are very interesting and are worth studying, or hopefully you'll come across them in some other classes. So I extract intrinsic dimension. And just as a quick poll, I'm just curious, in either this year's versions of data mining and ML or in previous versions, have you ever talked about any of these things? Local linear embeddings, isomap, Laplacian embeddings, manifold dimensional reduction, manifold learning.
Not in data mining.
Vaguely, yeah.
Yeah, we have talked about dimensionality reduction in data mining.
No, but I talk about manifold learning.
No.
No, those words are not familiar to you? Okay. We three of us should talk about this. Maybe somebody to throw this in because it's a very interesting topic, and it generalizes the tools that you have to think about the geometry of your data. So, okay. So these are, in my mind, at least three. And maybe by tomorrow there might be more. But reasons why we want to worry about embeddings and dimensional reduction when we're doing any data analysis. Now you got a question. Okay, is that good? Okay. Last time, we talked about a particular form of embeddings that are very popular, like I said, in theory work. And roughly speaking, they ask this following question. I have two resources at my disposal. Right? I have epsilon, which is used to denote the error in the way I do the mapping. Okay, I can always map everything down to one point, but the error is terrible. So that's one parameter that sort of holds me in place. I don't want to sacrifice error too much. Then there's, of course, the dimensionality itself, which is the other resource I'm trying to optimize. I do not want a high dimensional space. I want a low dimensional space. And both methods that I talked about last time are ways of saying, keep it fixed and optimize this. And I'm going to put this sort of in quotes because you're not technically optimizing this so much as just finding upper bounds on what you're doing, lower, upper bounds on what you're doing. Right? So in other words, for the two versions of the problem, the sort of general metric embedding problem, taking a metric and then embedding it in an Euclidean space, for example, or the Johnson-Lindenstrauss dimensionality reduction problem, which again you probably have all seen in some form or the other in other classes. What you're saying is that I want to fix the error. I want all my distances to be within 5% of the true value. Tell me what I can do. How well can I preserve the dimension in other data? And so we know for here the answer is if you want error log n, so the distortion is log n, the dimension is going to be log n. And here, if you want 1 plus epsilon, you can get log n over epsilon squared. I didn't prove any of these things, but I claim. Okay? And in all cases, you start off with this. This is the operator you're not allowed to change. This is the error I want. Tell me what I can do. Okay? And the methods we're going to discuss today, which are by far the, sadly, but by far the most common methods used in the actual world of data mining, we flip this thing around. What we say here is that you fix the target dimension, right? And you optimize. And again, I'm going to put quotes here because sometimes we don't really optimize so much as just try to do a good job. But again, the goal is that you fix the target dimension. And this actually makes a lot of sense, right? If you're visualizing, I don't care if you can embed this in 50 dimensions. I want 3. So my budget of dimensionality is 3. Tell me what you can do with it. Right? I don't care what you can do with 100. So it makes a lot of sense to say I want to fix the dimension. It might also be, no, I have some other reasons for believing my data is in fact k-dimensional. I have some other knowledge about the data. Find me a k-dimensional embedding. I don't give me a 10,000 dimensional, just because the error is low. So this is in some sense a dual way of thinking about the problem, and it does change the way you design your algorithms and the way you try to go about solving the problem. Because now this is fixed and this is not. Okay? And so now we're going to talk about this sort of alphabet soup of things. Right? How many of you probably heard of, at least, so how many of you heard of PCA? Okay, almost everyone here. How many of you heard of MDS? Not so many. How many heard of SVDs? How many of you think they're all more or less the same thing? I used to. Took me till last night to figure out they're actually not all the same things. So it's good to teach something to actually learn it yourself. Okay. So yes.
So okay. So this is very beautiful, right? I can technically say, oh, this is I have my metric space, I have distances, so on, and I have my epsilon, I have my dimensionality, and here's a bunch of algorithms that you can use, or you can write your own algorithm. But many times it happens that you don't have distances, right? So you have just raw data. you have, let's say, text, sentences.
Text. Yep.
Okay, and all you have at the end is, oh, I wanted the embedding, such embedding that, let's say, semantically similar word
Yep.
map close to each
Yes.
other. So the problem is much more unstructured.
Yes.
And so are we going to touch any of those topics?
In a sense, right? Because the minute you say, I want semantically similar things to be...
Let's say you have some objective function that you're optimizing at the end, but
Sure.
the input, it's
Yeah.
not so clearly nice.
It's not clear, it's not a metric space.
Yeah.
But what you typically have in many of these situations is, say, if not a notion of distance, but notion of similarity. You say, these two things look similar. These two things don't look similar. These two things look more similar than these two. So you have some number, usually. And if you don't, you come up with one. The first task of most of these problems is to come up with some quantitative way of capturing these intuitive notions of similarity. And this is not easy, right? Sometimes you make assumptions about this, and in a way that could be dangerous. But that itself is a process. It's a process that is, in some sense, either, depending on who you ask, the only problem in data mining, or a pre-processing step. For the people who think that's the only problem in data mining, they believe that feature engineering is the thing. And once you do the right feature engineering, your algorithms are trivial. You can do whatever you want. And there is a lot of truth to that statement, because if you get the right features, if my feature was the cluster label, I don't have to cluster anymore. Right? So in some sense, there is a continuum between the amount of feature engineering you do and the amount of algorithms you do. The truth is that for many problems, we have so much data and we have so little understanding that we don't know how to do good feature engineering.
Yeah.
So we offload the work out of the algorithm. And you're right that the more feature engineering we can do, the less work the algorithm has to do. But this is a much more unstructured task. I don't know a good way. I have not yet seen any good ways. I've seen chapters in books, but there's really very little you can say about a systematic way of doing feature engineering. For example, some of you came up with categorical data in your assignment. It's like, what do I do with this? It's a good question. What do you do with categorical data? Can I map them as 1, 2, 3, 4? Well, not quite, because that gives you other problems. And there's a whole discussion you can have on how to map categorical data to some numbers in a space, and how do you do it. So there are discussions of these things, but it's very hard to teach it. It's one of the things you learn with experience. And one reason I'm trying to get you to play with data is so you see all these problems at all. But no, there is no formal, structured way to teach how to do feature engineering, as far as I know. If I use Python, I would like to know more about that. And people who work with data sort of not just abstract points. I mean, I'm sure you can speak more to this point that how you do the feature engineering is a very ad hoc kind of use your brain, use your domain knowledge, and do something with it. I mean, you guys sort of work with a lot of data. Would you agree with that statement that the feature engineering is just a big mystery? You just do something.
I mean, what was I referring in my question for us? Actually, particularly to the fact that you don't need to do feature engineering. That you really start with your raw thing, right? So you start with your sentences, which are just tokens.
Yeah.
Right? And then, as you said, they usually define some kind of similarity.
Yeah.
And actually, if I think about, they did define, right? The words that are closer, let's say, to the center words are more important. And then let in this case, deep learning do their stuff to learn the meaning. And
so, by the way, deep learning itself can be viewed as a kind of feature engineering.
yeah, of course.
The claim, the successful, I mean, the more, okay, let's put it this way. The less overblown claims about deep learning are that what you end up with at the end is a set of good features for the data. And that's, I think, a reasonable thing to say about what it's doing, that is doing feature engineering. So one argument could be, okay, the answer to your question is deep learning. I don't think that's the right answer, but it's one answer. So anyway, so that's all I want to say about this at this point. I think we can talk about this offline more if you want to chat. Okay, so if we want to fix the target dimension and we want to optimize based on that, how do we set up a problem? Okay, so I think let's so let's see how we should do this. Yeah, okay. So we'll start with a very easy version of this problem. Okay, we'll start with principal component analysis. Contrary to what you might think, it is not principal component analysis. It does have principles, but no, it's principal. The notes I gave you to read actually have this spelling. That was fun. Because if you put this, it actually makes more sense. Principal component analysis. But no, you are finding the most important first. So in principal component analysis, what you're saying is that I have a bunch of points, okay, and they're in some Euclidean space. Okay, so we are not dealing with an arbitrary metric space yet. We will. But I have some points in Euclidean space that kind of scattered around the space. Let's say they in some stylized rendering, they look something like this. Okay. And what I want to do is transform the data, or transform the coordinate frame of the data, in some sense to capture where the data appears to be lying. Okay? So think of the exact version of this, where my data all in a line. Right? No data in history ever looked like this, but let's say you have some data that actually look like this. Then, oh yes, I want to know that line. Think of PCA as a noisy version of this problem. I have data that has kind of some trends along one dimension, kind of trends along another dimension, and so on and so forth, and I want to find these trends. Okay? Because if I now can transform my coordinate space, so this is my original coordinate space. Okay, my data looks like this. If I was able to transform my coordinate space so it looked like this. Okay. Okay, fine, I did a rotation, I did some scaling. Whoop-de-doo. Why do I care? Why do you think this would be a good thing to do? In other words, why do you think it would now be good to record the coordinates of the points along this direction and that direction? Especially if, say, I picked this direction to be the one that is spread out most along.
They're perfectly good.
Sorry?
They're orthogonal. They're kind of.
So is it here? This is orthogonal. What do you mean they are orthogonal? Can you be more, just be more precise about it?
Because I mean, if we're looking at like the data is kind of more, it's in line with the data, because the data is kind of going in a stream this way and then a stream this way, so I can represent them more in line with. So if I'm using this coordinate axis, I'm kind of summing along one and another to get to the data point, at least for most of them. Whereas on this one, it's a little bit, it's more off. I don't know. I'm not really doing it.
So you got the right intuition. And can you? So the question is, why is you have this sense that this is somehow bad, that they're going a bit on both is a bad thing.
Mm-hmm.
And what I'm trying to get at is, why is it a bad thing? Yes.
The thing is that if you rotate and use the other coordinates, you're going to do the least amount of error if you're going to use only the first, let's say in this case, the first.
Right, but this is kind of a retroactive interpretation based on the fact that we know what PCA is. I'm saying if you didn't know what PCA was, why might this be a good thing to do?
But we are capturing a lot of information in there.
Okay, can you expand that a bit more?
Because the spread of data is more in this dimension. So I mean, so it's a dimensionality reduction. I mean,
No, but why is it good that the spread of data is more?
Why?
Why is it good that the spread of data is more?
Because we will capture the more information if we capture this dimension.
So in particular, you're saying, suppose we instead projected things
if we project on this line,
like this way.
yes.
And you're saying everything gets, so you lose fidelity. So you want to get the spread to increase fidelity. Another way to think about this is that what we'd like, and this goes back to this point, you want coordinates to be roughly decorrelated. You want your features to be independent of each other, right? Because then you can talk about individual features as separate entities. It just makes sense to talk about on an orthogonal setting, right? Orthogonality should imply independence. Here, the features are orthogonal, but they're not independent. Here, they're orthogonal and they're hopefully independent because you see variations along one but not the other. So even if you did no dimensionality reduction at all, it would be better to have this frame versus that because you have independence of your features. And this goes back to the thing you were saying about they're moving in both directions at the same time. And now getting to the point that both Clement and Raghavendra are making, right? If you now choose the appropriate dimension in this way to increase the spread, then now you're hoping that your error has reduced because you captured the maximum amount of information. So there are kind of two things going on here. One is that you want to get orthogonality, and one is that you want to maximize spread.
Why they're orthogonal?
Why orthogonal?
Yeah.
Because I represent my features as a vector. A vector has coordinates,
That's
and I want to treat the coordinates as separate entities, that each feature itself should mean something to me. The point of PCA is to say that each independent feature means something.
But they are not independent. It's an ellipse. An equation of
It is noisily independent. I mean, you get more independence this way than you would get this way, yes. I mean, think of this as an approximation of this line. Now we have the clear the dependency structure of the data is much clearer in this setting than in the original setting. Because now I have independent features. I can express x and y as separate meaningful entities. Okay. Because we believe orthogonality is important. Okay. I mean, there's something that's kind of baked into the way we think about data, right? We automatically put features. we say, okay, we'll just slap on these features. We never stop to think if they're actually independent of each other or not. PC is a way to make sure they are, to decorrelate things. Okay? All right. How would we do this? If I have a bunch of data and I want to find the direction of maximum variance, right, where there's the most spread, okay, how would I do this? If I write this down as an expression, so I have some direction u, so we'll think of u as a unit vector, right? And I want to say what is the maximum variance along this direction u. So how would I measure this? So to get if I want to project the data point along u, I could do something like u transpose x. That would give me the amount of projection of x along the direction u, right? And I can say that, okay, I'll look at the total amount of variation, and, and take the average. Okay. This is now squared, right? This is basically this captures my variance along direction u. Right, so this is the variance at u. Okay. What do I want to do now? I want to maximize this one. So I want to maximize over u 1 over n sigma transpose xi whole squared. So using some basic sort of vector magic, you can rewrite this whole thing as maximizing over u. I'll ignore the 1 over n because it doesn't really matter. Sigma u transpose. Okay. Play this right. Okay. Now this, of course, is a constant. It's an input, right? So just call this capital X. So we'll maximize over u transpose x u. This one makes sense. Okay. Where let's see. So x. Let me see if I get this right. I always get confused. I think it should be a matrix where xi transpose. So basically, if you think of xi transpose, yeah, so it'll be the matrix consisting of the ij at entry will be xi transpose xg. Sorry, yeah, is that right?
So matrix.
Huh?
Is with the matrix.
Yeah, a little bit. And again, if you actually, maybe we should put the 1 over n back in here, because it gives a nice name, which is a covariance matrix. Okay. So now we've taken one maximization, which looks cryptic and funny, and replaced it by another one that looks cryptic and funny. So progress. What do you do now? We make an observation that this matrix, well, we don't have to make any observation. What is this doing? This is a very natural sort of thing that leads to another well-known thing. I'm being vague because vegetable things are. This is one of the most basic objects of a matrix is defined in this way. So they are
You are multiplying a matrix by a vector, right?
Yep.
Yeah.
So U is a vector. I take a matrix, multiply by a vector, and then do U transpose. This is one of the most intrinsic properties of a matrix comes from this expression. Sorry? No, the matrix is arbitrary. No, the U that you produce. Okay, let me just replace this. Let me say I want the U itself. It's a very important quantity.
This entire thing is very important quantity.
It is because I say yes. But it's a very, what I tell you is like, oh, of course.
Is this again wild guess? Eigenvalue?
It is, it's an eigenvector.
Eigenvector.
It's the eigenvector corresponding to the largest eigenvalue. Why? So let's take any eigenvector of x. Okay, let's take an eigenvector. Let's say we have a lambda v eigenvector eigenpair. So what is x times v? By definition, lambda v, right? Okay, so assume this is normalized, so it's unit vector. So x times v is lambda v. So you get v transpose lambda v, which is equal to lambda. Right? So if I maximize this quantity over any u, what am I going to get? I'm going to get the maximum eigenvalue, and the thing that gives me that is going to be the maximum eigenvector. So if you do this thing that we wanted, if you wanted to find the direction along which you get maximum variance, that direction is the eigenvector, is the largest eigenvector. When I say largest eigenvector, I mean eigenvector corresponding to largest eigenvector of the covariance matrix.
Can you explain this point?
Which one? Here? Okay. Take any eigenvector of x. By definition, x times v is lambda times v.
Yes.
This is a vector, this is a scalar. This just comes out. V trans I said v is or as a unit vector. V transpose v is 1. Okay? So this gives you the largest eigenvalue and corresponding eigenvector. And now we actually know what that eigenvalue is, right? What is the meaning, the physical meaning of that eigenvalue, that number? That is in fact the spread, right? So you know exactly what's going on. So this isn't, now once you have this, you can do the next one, and the next one, and the next one. So in general, if you compute, so if you take, so PCA basically boils down to compute the covariance matrix of x of x, right? Take the eigenvectors for the top k eigenvalues. That's v1 up to vk. By definition, these will be, now let's forget this. Okay, because x is positive definite, because this matrix is positive definite, and you can verify this, these will all be orthogonal. So this gives you a frame of reference, and that's your space you project it into. You take the top k because they give you the maximum variance in degrees. In fact, you can show that over all matrices of rank k that claim to be a basis for what you want, this is the one that preserves the most amount of your information. It minimizes the error in a certain way. So it has very nice properties. This is PCA. And so in particular, if you have some data and you clustered it, you have some data, you want to visualize it, what would you do? You would take the top two, the top three, and then take the numbers you get from doing that projection and then put it up on the screen. So in particular, if you actually wanted to get the coordinates, what you say is that, okay, I have some point now. So I have some point x in a high dimensional space. I want to get its coordinates in this frame. So what I do is I take my new coordinates of x, so the k coordinates. The first coordinate will be v1 transpose x, v2 transpose x, v3 transpose x, up to vk transpose x. Why? Because what we're saying is that remember we said the projection of x along the first direction was basically this quantity here. So you're just projecting along a line, getting a number. And this number could be negative or positive, doesn't matter. So these are the coordinates. So for each x, you get its representation, we'll call it y, in this lower dimensional space. So now if I just take the top two, I now have two-dimensional coordinates for every point, and I can plot them. That's PCA. And again, PCA is not just used for visualization, it's used to basically compress your data and you try to understand. So for example, you might say, okay, let me look at the representation I get from the top 2, top 3, top 4. You could imagine that as I get better and better, my error of my measurements go down. Maybe there's some point with a huge dip, like, aha, my data is truly k-dimensional, I'll go pick one. So there are many things you can do with that information. Did you have a question? No. Okay, any questions so far? All make sense? once you have PCA in your arsenal, so it's funny actually. Last night I was googling sort of just trying to sort of get some sense of what is the difference. How what do people say about the difference in MDA and PCA? So I googled it, MDS and PCA. There's a ton of questions. What is the difference between MDA and PCS on Quora? What's the difference between MDA and PCS on Stack Exchange? There's a lot of questions like this. So hopefully today I will answer that question for you, so you don't have to ask it again on the web many more times. So some of you have heard of MDS, and there's some small fraction of you who heard of both MDS and PCA. So does anyone care to hazard a guess as to what MDS is? The ones who put their hand, I said, have you heard of MDS? See, I should have kept track of who they were. Because now if I say put up your hand, who's the put up their hand? Sorry? What is the full form? Great. What does that mean?
I don't know.
Yeah.
Think about it more so.
Anyone else? MDS, anyone?
What was the question? What's the difference?
No. Wait, first question is, can you tell me anything about MDS? What is it? I don't want, it's a method to dimensional reduction. Yes, we know that. But what does it do? Well, anyone?
I think you have a matrix of distances.
Yeah.
You compute the covariance of these distances. You compute the covariance of this matrix, if I'm not wrong. There is some centering step.
So you're describing an algorithm.
Yeah.
I don't want algorithm, I want the problem.
Uh-huh.
We'll solve the problem later. There are many ways to solve the problem. What is the problem? But it's interesting that you know the algorithm, but you can't describe the problem.
No, because I was looking at that algorithm that you described last session.
Ah, okay.
And then I came across something.
These methods have been used in marketing for last 35 years.
Right.
PCA and MDS. And I can tell you the usage, how we make the usage, and that's probably explains some bit of differences.
Yeah.
This we use a lot of time when we have lots of scale items and we want to compress them for dimensions.
What do you mean scale items?
So many times you go through these personality scales where people say how much you like this and measure different.
Yes.
And then you run through PCA and you find out some common core. So this is related to people's emotional reaction to this or their satisfaction. So PCA is used. This one we do more for quality perceptions. You ask people about brands that you think how similar is Mercedes to Toyota or this and that. You do a lot of these comparisons on various dimensions, and then you want to see where do we see these things together. So is Mercedes more similar to Toyota if you compile all these dimensions, or more like a perceptual map if I want to get inside your mind to understand.
So why would you not use PCA for the second?
The problem with PCA we run into most of the time is that even if you come up with those dimensions, it's very hard to give a label to those dimensions.
Why do you need a label?
Because if you want to visualize that information to understand, you just want to see whether these two things are coming together more like a clustering problem. Are they similar to each other or are they different from each other? So when we want to extract some higher dimension, so lower dimension commonality, we do this. But if you want to get into just some form of a similarity, when something was spread on many dimensions, we use MDS.
Okay, good. So when you first started explaining this, I was getting confused, but I think now I'm beginning to see. Okay, so right, this is good. So so what you're saying is there's some sense in which you're using PCA to get low dimensional structures. You have some information, you want to just bring it down, and that's clearly what it does. But MDS is to just find something interesting, some kind of connection. This is good, because in fact MDS starts from fewer base assumptions and knowledge about your data than PCA does. In fact, as Meena said, MDS starts with a metric only. All you have is a matrix of distances. So the MDS setting is the following. Rather than having points lying in a d-dimensional space, all I have are distances. I have, say, a metric. Okay? So I have some kind of metric, and of course I can describe a metric by a collection of distances. So n cross n, I have dij. Yes, and of course this matrix is symmetric. It's symmetric, so dij is equal to dji, so on and so forth. And this will have zeros along the diagonal because we expect that from a distance, right? And as Himanshu said, right, all we want is to get some kind of better structure or feature representation for this data than we get. Distances are not very useful. If all I can say is how far apart you and I are, that doesn't say anything about where we are situated in space relative to two other people. right? All I can do is measure distances. It doesn't tell me much. So the question is, can I extract a representation of this in a form where instead of my existence being defined by distances, is defined by myself, by my coordinates. In other words, MDS is a way to construct an embedding from a metric space to a vector space, in particular Euclidean space in this case, at the top. So again, go back to the analogy we had there before. Even in the case when we were talking about, fixed epsilon optimizing the dimension, we had two flavors of the problem. One was I have an arbitrary metric and I want to embed this in the Euclidean space. And one is I have a high dimensional Euclidean space, I want to embed into a low dimensional Euclidean space. So you can think of the analogy here as very similar. Right? This is the kind of MDS version of the problem, and this is the PCA version of the problem. Right? In PCA, you already start off with data that you believe to be in a Euclidean space. Why? Because none of these operations would make sense otherwise. I cannot take inner products unless I have a Hilbert space, or in this case, a Euclidean space. I'm not allowed to do things like this. They have no meaning. So I must start off with the Euclidean space and then bring it down to size. MDS is a much more general hammer. It says, I don't know anything about my data, I just have distances. Tell me something I can do. Okay? So if, for example, you have some similarities, you don't have a vector space, you have some notion of connection between these. I'm going to try and do this. So this is the strategy. Okay? And now the question is, how do you do this? Again, the goal is to come up with some fixed target space and do the best you can. All right? Okay. So, the idea of doing MDS, and again, is to go to an intermediate representation, is to go from distances, which I don't like, because it's kind of a negative view of the world, how far away you are from it, to similarities, which is a positive view, how close you are. So what I want to do is go from distances between objects to similarities between objects. Now this seems like a silly thing, right? You take some large value, you do large value minus distance, that's a number which expresses how close things are. Done. Sure. But you want more to it than that. What you want is this similarity matrix, Sij, so the similarity between Si and J, so you would ideally like these things to be 1 here and so on and so forth. What you want for it is to have some more structure. In particular, you want it to have something called a positive definite structure. This matrix. And here's why. Suppose I was able to construct a matrix of similarities that in some way captures the opposite of distances that have been given. Right? So things are closer if they're less far apart. And this matrix happened to be positive. Let's say I magically was able to do this. So let's call this matrix S. If it's positive definite, I can write it in the following form. Right? That's any positive matrix can be written in this form. Usually there's a diagonal matrix in the middle, but since it's positive definite, all those eigenvalues are positive. You can take the square root and you can push it on this. So you can write this. Okay, but now what? What is this matrix? If you think of this matrix now, the entry Sij can be written as the dot product of Vi and Vj. Right? But now we're in business. Because if I have distances, if I have similarities between things measured as Vi and Vj, I can now write the distance between two things in this new space as Sii plus Sjj. This will be x squared plus y squared minus 2x dot y. Okay? And again, if you plug in Euclidean inner products in here, you get exactly x minus y whole squared. And now I have a distance generated from this. What's more now, this distance will in fact be equal to, if this in fact is this, it will be equal to Vi minus Vj. Okay, so what have I done here? What I'm saying is the following. I can actually construct an embedding of the distance matrix into points, actual vectors with coordinates. If somehow I can magically construct an S that preserves this relationship to match this value. I obviously can't do this because this is going to be approximate, but this is what I want. So if I can take my distances, make them into similarities, and then do some magic on the similarities to get the best possible vectors to capture this quantity, then I have an embedding. This is the basic idea of MDS, that you take a collection of distances and you treat them as if you really wanted them to be Euclidean distances, in which case they must satisfy this property with equality, but they don't, so we'll find the best fit of the square peg into this rubber. I'm going to do this in much more detail, but this is the high-level picture. So if you have any questions, this is a good time to sort of say, okay, this doesn't make any sense. How do you come up with this stuff? Distances positive. That's the magic. It's a very clever trick. I'll show you in a second. I mean, in some sense, I've told you what to do, but to make it in matrix form is a bit tricky.
And that will show that it is positive.
Yes. In fact, that part I'm not going to prove, but actually, am I going to prove? Yes, I will. I can prove. I'm not sure. Well, I'll see. Any other questions? Okay, so how do we do this? So the first step is to get this. So there are two parts to this. How do you get this? And how do you go from this to something reasonable? Right. So here's what we're going to do. Let me see. So the first magic step we're going to do and I should say that this process is going to minimize the following cost function. I should have said that first, actually. I've done the same chapter. What I want to do is say, okay, I have the dij's, and I have the distance vj, vi minus vj whole squared. What I want to minimize is this quantity. So sum over I, sum over j, dij squared minus I want to minimize the squared difference between the square distances. Actually, no, sorry, I made a mistake here. You don't need the squares. So this is a very reasonable thing, right? What I'm saying is that on average, I want the distance in the target space to capture the distance in the source space. On average. Okay? I go square because I don't care about signs. I can take absolute values of it. That's called robust. Notice the difference between this and the methods we talked about earlier. Here, our notion of error was not this average notion, it was a worst case notion in terms of ratios. What is the worst case ratio between two things? Here, it's more like an average difference between two things. And this is just in some sense, a stylistic concern. Those kinds of ratios are easier to analyze, so it's much easier to prove bounds for those kinds of methods. It has been notoriously hard to prove anything for these kinds of measures. And I don't think to this date we actually know formal guarantees on what we can do for MDS. This is an open question in my mind. But you know, it's more sort of smooth than this. That worst case methods have outliers and stuff, and in practice you might not want to use that. But this is an open question if anyone's interested. In fact, one of the faculty candidates we have coming in 2 weeks from now, part of his work is basically saying, okay, take these standard, not this one, but standard algorithms that people use in machine learning, can we actually analyze them and explain why they do well? So that's kind of an interesting line of work. So we have a bunch of sort of theory of data faculty candidates coming in next month. Okay, so this is what you want to optimize. This is the plan to go about doing this. And the question is, how do we do this? So the first thing we're going to do is create this matrix S. Okay? And here's a magic step here. And I've been thinking about the best way to explain what this magic step is doing, and I don't think I've succeeded yet. So I'll toss it out there, and maybe you can come up with something better. So the idea is that this matrix S, I'm just going to define it. Okay? I don't really like it, but I'm just going to define it. Okay? So we'll call this matrix, this is D. When I say D squared, I'm going to mean by putting the squares on every element. So it's an element by, it's not, so I'm just going to put D squared here. It's not a square of the matrix, but it's an element by element squaring. Okay? Where H is equal to the identity matrix minus 1 over n, the all ones matrix times this transpose. Okay, so what does this weird thing mean? This matrix H looks like this. So it's identity, so it's got ones along the diagonal and zeros everywhere else, minus that thing. That thing is basically 1 over n, it's a matrix full of 1 over n's. But if you think of the all ones vector, which times the all ones vector, you get an all ones matrix, times 1 over n is just all 1 over n's matrix. You subtract the two, you get something like this. You have 1 minus 1 over n up top, 1 minus 1 over n, all over n. And everything else is minus 1 over n. Okay, that's what this matrix is. And the claim is that if you do this operation on D, what you get is a positive matrix. I'm actually not going to prove that it's positive because I'm not sure I can right now. I was trying to prove it in the car on the way here. It's always dangerous.
D power 2.
It's not D squared. It's the pointwise squaring of every element in D.
Yeah, that thing.
Yeah, so it's you need to. Otherwise, if I said just D squared, it's like D times D, which is not what I'm trying to say. Yeah. Okay. So in other words, just think of the square of the distance matrix. Don't think of the distance matrix. Just think of the square. Okay. So what is really going on here? And it's helpful, and I'll give you some rough intuition of what's happening. If you think of just D to H, it's helpful to think of what this is doing. Okay? If you now do the multiplication of this with this, let's look at the first entry of this resulting matrix. Okay, what does the first entry look like? So you're taking the first row of D, so that's distances from the first element to all other elements. And this matrix is symmetric, so it doesn't matter. Okay? So looking at my distance to all of you, that's my vector. So my distance to myself is 0 and everyone else is there. Right? And then I'm multiplying it by this, which is 1 minus 1 over at the top, and everything else is 0. Everything else is minus. So it's basically saying it's the distance to II, which is 0, we'll pretend that, ignore that, minus 1 over n times the sum of the distances dij for j equal to 1 to n. D11, I should say. Right, that's what's happening here. Because you get a 1 minus n for the first term, and you get a 1 minus n for everyone else. And you just get a 1 for the first term. So that one goes up there. Okay, so that's the first term. What's the next term look like? The next term is, so what's going to happen is that D12 is going to get promoted to the top. So there's going to be D12 minus, again, 1 over n summation j equal to 1 to n d1j. So if you think of this in sort of horrifying MATLAB notation as the average of D1 dot, it's some kind of weird centering operation. You're taking every distance from me to someone else and subtracting the average distance from me to everyone else from it, and you get this whole question. And then you fill this in.
So isn't it D squared?
Oh, I'm sorry, you're right. These are all squares. Right, thank you, thank you. Yeah. So it's the average centered square distance. So you take my distance to you subtract the average of the squares of the distance of everyone else, and so you get a whole bunch of numbers here. And if you do it on the other side, you do the same thing along the columns instead of the rows. And so what you end up with, if you want to write down, so I said that Dij is equal to Sii plus Sjj minus, what did I say? 2Sij, right? Yeah. Yeah. If you flip this around and say, okay, what is S in terms of D? It's not hard to see that if you want this property to be true, all you need for S is that Sij should be equal to some constant, some scale constant, which we'll have to put it later, times, let me see, what is the right expression? It's something like,
So I want, okay, so what I want is that Dij should be positive. So it better be negative. So something like this. Some constant that depends only on I, plus some other constant that depends only on J, minus some global constant, K, minus Dij. Okay. So it turns out if you plug this quantity in there, as long as I give you these constants, this will work. Okay, this actually should be again, you have to plug this in, but if you see this, if you do this thing, so what's going to happen is that SII is going to be CI plus CI minus 0, minus K minus 0. This is going to be CJ plus CJ. That's going to cancel and that's going to cancel this two terms here. You're just going to left with Dij. You can plug this in. My point is that this is what you want Sij to look like. What you actually get from this construction there is very specific values for these things. So this is going to be the average distance squared. Sorry, I keep writing my square. This is going to be the average distance squared from I to things. This is going to be the average distance squared from J to everything. This is going to be the overall average distance for all the points in the set. So if you work on that expression for that, this is what this will end up being. I worked this whole thing out and I got this. I said this doesn't make any sense. And I realized you don't actually need any of this for this to be true. But I think for this to be positive, definitely you need these to be these particular values here. Okay, so that's, in some sense, I'm trying to give you some intuition about what this value looks like, this similarity value. It's something that, of course, depends oppositely on this, which is how it should be. Wait, there's something wrong. Maybe I got this. I want this to be negligible. So if the Dij is large, the Sij should be small, and so on and so forth.
So this definition, A minus.
I'm not done yet. I've got a long way to go. All I'm doing so far is constructing a similarity matrix from D automatically. So you're asking about how do I automatically do that? This is how you automatically do it. That thing gives you the property of this whole thing.
Every element of S,
Yes.
let's consider Sij.
Yes.
Will give me this expression only.
What do you mean? Will give you this
I mean,
equation? Will give you this.
When I calculate the matrix here,
We will look like this.
let's suppose we are here at this point.
Okay, we're here. Yes.
Okay. We calculated S,
Yeah.
and this matrix we got.
Well, this is the first part. This is just D times H, and you multiply again by H again on the other side. Then that's why you get this one.
Oh, okay, so we will get one more term?
Yeah, you get, so you average this thing now.
Okay.
So that's what's going to happen is you're going to get this term. You're going to get the average of this. You're going to get the average of this. The average of these guys along a column is going to give you this overall average. The average of this guy along a column is going to give you the second term here. And you have the first term already. So that's why all these terms show up.
There are only 2 terms and there are 3 terms. So
I know, because I only did one of them.
It's okay.
Yeah, I don't want to write on the other H. You have to do this whole thing get multiplied by H. And then the minus half. Okay. So all this is doing essentially is centering it and giving you this kind of similarity structure to this. Like I said, anything you put in here would work, but this in particular, I think you need for positive. Okay. Okay. So this is a mechanical construction. If you think of it from an algorithm's point of view, all I do is take my distance matrix, square all the values, compute this S. I don't have to think about anything else. It's very easy so far. I'm not doing anything clever yet. So now I have S. Now what? First, I think I'll go back to the other side. Yeah, I'm still a little bit annoyed, I have to say. I'm unhappy that I don't have a good intuition for what that thing is doing. But I'll think about this some more. Okay. So remember we had step 1. Compute
D2 is equal to the set of all DIG squared. Okay. Then step 2, compute S is equal to minus half H T H, where H is equal to I minus 1 over N 1 transpose. Right, so I'm trying to make this clear. That's not just the number 1. It's a vector of all ones. So maybe I'll just write that here. Yes.
Is there any specific reason why S is equal to minus half X?
In order to get A, this property that we want,
Yes.
which we could satisfy with anything of this form, but also to get this specific form.
That's why that.
Yeah, and I think you need it for the positive, unless you want to get it.
You want the S to be symmetric,
Yes.
positive, definitely.
Yes.
So that they could neutralize
Yes. Yeah. So you need S to be PD. So the S part would be easy. The PD part is what you need this construction for. This is the magic step that I'm not happy about. I don't have a good answer for it.
Nobody can dream of this thing. That why.
No, we can. You just have to.
No, you will see now. You will see now. You do the choice.
No. But that's not the point. The point is not that it becomes PD. That we agree on that. How do you decide that this is how you want to do it with the class?
Yes.
And like I said, I will think about this. There is a way. I've been playing with this, and there is an intuition for what's going on here. I don't have a good one yet. So I tell you, I'll just confuse you right now. But you should all think about this. It's a good question. Why do we do this? Because you don't need all of this magic to get this property. This is the only property we cared about, right? At least I claimed we cared about. And you can get that with anything you want here. I can put 0, 0, 0 here, it'll still work. But my conjecture is that if you want positive definiteness, you need to have this particular form, or some form like this. Maybe not this exact, but something like this. And this is the most convenient one. And I would encourage you to at least think about why that would be. Okay. So, and I'll also think about it, both mathematically and intuitive, what it should be. So, okay. So we got this step. So far, our algebra is here. We got S. Now what do we do? Now again, we know that we claim that this matrix is positive definite. So I can rewrite S as some X transpose X, right? So I'm done, right? Am I done? I have my vectors. Why am I not done?
Will ensure that this property. That has to ensure this.
I have it. It's 0. It's exactly the same.
See?
Yeah, it's the same. Those x's will follow this exactly. 0 error. No problem at all. This is not a trick. That will exactly give you this. But there's a problem. Remember why we're doing all of this. Why are we spending all this time and effort doing all this linear algebra that no one told us we should learn in undergrad?
The vectors are very big.
Ah, how big are they?
Well,
What is the dimensionality of any vector you get from this process?
it's n.
It's n. Whoa! I took n squared distances between n objects and I gave it an n-dimensional vector. This is completely not awesome. I have a huge dimensional representation now. Remember, my goal is to get a low dimensional representation. This operation only guarantees positive definiteness. It doesn't guarantee me positive definiteness and low rank at the same time. That's what I have to do now. In some sense, I have done the step that gets me to PCA. Because I've constructed an n-dimensional explicit embedding into a Euclidean space that is isometric
And this is the starting point.
of PCA. And in fact, that's what you do. It's slightly different technically because PCA is dealing with D cross D matrix as n cross n, but what you do is again, so let me spell this out, but this is an important observation that we've now got ourselves to the starting point of a PCA-like step, where we have an n-dimensional space, and we want to project things down to some k-dimensional space, right? So we already have the covariance matrix for free, right? What we want is some embedding into a lower dimensional space, like this is what we want. So technically, you want to, so you can think of this as saying that
you have this matrix coming from the n-dimensional data, and you have some other matrix that comes from, say, low-dimensional data, where each of these is of dimension k. So think of this as n cross k, k cross n. So this is also n cross n. Right? So all the covariance is coming from k-dimensional points. And you want these two to be as similar as possible. Right? So you want to minimize something like this, right? Yeah, so you want to minimize the trace of this quantity. This is how we do matrix minimization. If you want two matrices to be very similar, you minimize the trace of their differences. Okay. And again, not surprisingly, you can use the SVD to solve this problem. Basically, what you're saying is that what you want is, okay, so the derivation is actually in the notes, but I can just sort of jump ahead and say, what you're trying to do is minimize this quantity. You can write this as, let me see what the best way to say this is that. Yeah, because x transpose x by definition is positive definite. Okay, I'm going to use that factor given to construct this. We can write it as some kind of v gamma v transpose. And because y transpose I by definition is positive definite, any matrix form that way has to be positive definite. By the way, do you know why that's true? If I take any matrix and do y transpose y, it has to be positive definite. Do you know why? I mean, think of computing.
But it's an even product with vectors.
No, this is a matrix.
Matrix is not
It's a matrix of inner products.
yeah.
So why should a matrix of inner products be positive definite?
It's
like square.
Of all these different. It's
I
like
don't know,
for
what is
any
it?
vector x, a matrix A is positive semi-definite. Positive definite. If for any vector x, x transpose times A times x gives you a positive number.
Correct?
Okay. Now, if you multiply this y transpose y by a vector, what is it? This is exactly the norm of y u squared.
Thank you.
That's what it is.
That's it. So if you just write this out, this becomes the norm of yu squared. It's a square, therefore it's positive. Therefore this is positive. Thank you. Okay, so just a minor point. Right? Any matrix form has to be positive. So I can write this in the form, again, I want to use the notation. Right? And so what this boils down to, these are all orthonormal. So what this boils down to is that if you want to minimize this quantity, what you're really minimizing, because you can play games with your trace now, is basically you're trying to minimize the trace of this gigantic expression. And this is where you start glazing over because of the number of matrices in the function. Don't worry, it happens to me too. There's this cool thing with the trace that you can kind of rotate the multiplications in the trace and the trace remains the same. So we're actually going to just multiply everything by, we're going to flip this around. It can be written as the trace of this diagonal matrix minus, let me get this right, V transpose Q transpose squared. Okay. Oh, then I have to put a V in here. Okay. Actually, you don't have to do anything clever here. You just sort of pre-multiply and post-multiply. Did I get this right? Should have been the other way around. But okay. I'm just following the notes, so it's easy. Now this quantity, we'll call this G. And this becomes G transpose. Right. So this whole expression now becomes, and again, bear with me, okay, because this is a bit of algebra. And I never have ever done this algebra, and so I always have this only vague understanding of how this works. It's actually helpful to go through it and see the details, so you actually see how this works. So you end up with this trace of this diagonal matrix gamma minus G transpose whole squared. And you're trying to minimize this over, what are the unknown quantities here? Over this and G, right? This is fixed. Oh, sorry. No. Till then. Because the y's are the unknowns. X is given. So it turns out it's not hard to see that if you fix any particular value here, the best thing you can do for G is to make it identity for any fixed value of this. So for any fixed diagonal matrix that you want to search over, the best thing to do is set G equal to 1. I mean, set G equal to I. And then this becomes the trace of this minus this whole squared. Okay? And then now we can say we want a k-dimensional representation, remember. And again, a simple trick. If you have a matrix and you want it to be k-dimensional, all you have to do is make sure that only k of the diagonal entries in this middle matrix are non-zero. Because if you think about a matrix here, so I have some matrix, I have a diagonal matrix here, and I have another, the transpose of that. If I nuke everything above this to 0, it'll just cut off everything else. This will be a k-dimensional representation. All of this will be zeros. So what this is saying is that just if you want to minimize this expression, make sure this contains the top k values of this in descending order. Okay? And once you do that, G is equal to I, but G was equal to V transpose Q. Well, we know what V is. V is given to us. So we know what Q is. This is equal to I. So we can solve for Q for this. And what you get is that, let's see. So G is going to be, yeah, so that means that since V is orthonormal, Q is equal to V. And what essentially is, what this is saying is that if you want to get a best k-dimensional representation of your similarity matrix here, just do the SVD of X, which is basically the eigendecomposition of X transpose X. Take the top k values here and the corresponding vectors, and that's your representation, which is exactly what you do in PCA. So the intuition was correct, that you just are in a PCA situation. You're doing something subtly different though. You're minimizing the difference in the similarities. And this is the thing about MDS that's a little known, right? People say, okay, MDS is doing this kind of distance preservation. What it's doing is preserving the similarity difference. And you want the similarities to be the same. And that's when you get this whole derivation. Okay, so MDS has 2 steps. Step 1 is to do the transformation into an n-dimensional space, which is this, and then project that n-dimensional space down to k dimensions to get this. And you end up with basically, compute SVD of X and take top k singular vectors. So that's where the whole PCA, MDS, SVD sort of trinity comes from. They're all related to each other. Again, there's all the notes that I put up on the page. Okay. And once again, if you want to render the result, you just say, okay, I want the top 2 dimensions, top 3 dimensions. In fact, this is one of the more popular uses of MDS, to just visualize the output. Because again, for an MDS problem, you have a much more general input. You might have just distances. You might have, say, for example, a very common use of MDS is I have landmarks in some space, and I measure the road map distance between them, and I want to plot them. And the space is more complicated. It's not a map, it's only one wall. So you plot them and you spread them on nicely. It has its limitations. It's not the best one out there. There are better ways of doing this embedding, but it's definitely by far the most popular one. And a lot of times when you compute your clusterings, at the end of it, you will do some form of PCA. All right, questions? So this, I think, concludes our brief interlude into dimensionality reduction. From next week, we will return back to other clustering formations. But I want to do this as a thing in the middle, just to keep, so because, in fact, for some of the assignments, it's going to be handy to be able to sort of say, okay, I can visualize the output. The next time we'll explore some basic tools. Okay, questions about any of this? So hopefully now when someone posts a question on some forum saying, what's the difference in PCA and base, you can actually be the one to answer.
That is for minimizing the trace for fixed value of
yeah, for fixed value of lambda tilde. Yeah, actually lambda, correct. Lambda tilde. Yeah.
So the G has to be 1.
Yeah.
I mean, identity matrix.
Yeah.
this is true.
You can differentiate this.
Yeah.
So if you do some boring matrix calculus, you can do something. One way of trying to prove this is to say that the sorry?
I mean, multiplying it by that value, if we keep anything G as like anything else other than identity matrix,
Yeah.
will it increase the value of that G?
Yeah, it's kind of
Is it the inclusion or what?
yeah. That basically sort of because of this, because you're basically getting a square. It's kind of pulling things apart. That's the intuition. I mean, I think you also need the fact that G is orthonormal. So you can't play scaling tricks
Okay.
among all the orthonormal matrices, because see, these are both rotation matrices, right? So this will be as well.
So it's the same ultimately, Q is same as.
Yeah. So there will be rotation matrices, right? So I think that fact is important. Otherwise, you could do some cheating scaling tricks and make it look like it's small. But I think G is, given that it's orthonormal, then all you have to do is return. And so intuitively, what you're saying is that you just want to transform it so they just point in the same direction, which gives you. So I have to think about that. Yeah. Any other questions? What any of this so far today? So you will find a lot of clustering algorithms in the literature that basically, after a lot of mumbo jumbo, boil down to run PCA and do something on motivation space. And a lot of times, it's all muddled together in the whole description. And somehow, I guess people didn't see that, but that's what they were doing because it's all muddled together. But if you look at it very carefully, it's like, okay, you just projected using PCA and then you just ran a clustering algorithm. In fact, we will see algorithms later in the class for spectral clustering where you do basically that. You do a form of MDS, a special kind of MDS. So you embed into space and run k-means. That's your spectral clustering algorithm. So all the work is in the embedding. There's nothing else happening on it. Okay, but it's a very clever kind of embedding. All right, if that's it, then I guess we're done for now. See you all next week.